Hello everyone, welcome to today's webinar, FEA-driven design of load-carrying structural parts. Designers of load-carrying structural parts are faced with ever-increasing requirements related to lightweight and structural durability. This means getting a low-volume design with the lowest attainable stress levels and remove stress concentrations. In production environment, this can only be achieved by engaging a highly efficient and fully interactive topology optimizer like ProTOp Professional. And today's presenter, Marco Kegel, devoted most of his 30 years long career to computational mechanics. His current work is focused on the development of parallelized and efficient numerical algorithms involved in modern structural topology optimization processes. And now let me tell you a little bit about Novedge. Novedge is one of the largest online stores for design software. And not only we offer you just assortment of software solutions, but also you can talk to us. You can call us at any time and we can really help you figure out what you need and how best you can get it. Go to novedge.com and call us. The number is displayed on every page. And for more daily software news and limited time promotions, pay a visit to the Novedge blog and follow us on Facebook, Google+, and Twitter. Coming up in our next Novedge webinar, discover the new tier render for SketchUp. Last but not least, today's webinar is being recorded. And if you want to rewatch it, you can go to the Novedge's YouTube or Vimeo channels. And now, without further ado, I'm going to pass the baton to Marco, and he'll show you all about ProTOp Professional. Take it away, Marco.
Okay, thank you, Barbara. Hello to everyone. I will just start with explaining a little bit about the content. We will start with the basic assumptions so that it will be clear completely what I will be talking about. Then in the following, I will spend a few words on topology optimization, because this will be actually the fundamental, the underlying tool that will be used here. Now, of course, the main part of this presentation will be how to engage topology optimization successfully. And at this point, I would like to note that the software that will be used is a standalone topology optimizer KS ProTOp, and the simulation that will be run will all be run live, so I will not use any pre-recorded animations or something like that. Okay, let us just start. To the assumptions. We assume that we have to design a load-carrying structural part, and let's say the basic requirements are that the part should be lightweight and durable. Now, in the mechanical context, lightweight is typically translated, let's say for a fixed material, into low volume, and durability is typically translated or mostly translated into getting lowest attainable stress levels, and which is very important and critical, removed stress concentrations. This is very important because we know that otherwise a well-designed part can, if it exhibits only one stress concentration, this can very quickly lead to crack initiation, and once this happens, the crack will promote and eventually destroy the part. Okay, now to meet these mechanical requirements, we have, of course, the traditional option to do the design manually. This is a cycle with running FEA and changing the design. And if we have a real three-dimensional part with many load cases, this becomes an incredibly difficult and tedious task. So luckily, the tools that are developing in recent years, like topology optimization, can help a lot. Now, unfortunately, what we can see from our experience is that topology optimization is often misused or not used correctly, and people often end up with the conclusion that this is something that it is not usable in practice. Now, I hope I will try to convince you that this is a very usable tool, and of course we have to learn something and we have to use it properly. Now, a few words about topology optimization. I don't know what is the level of knowledge about this theme, but okay, I will be short. From the numerical point of view, topology optimization is actually, we can say, a process of finite elements removal or later restore by some numerical algorithm. So the set of all finite elements in a model with supports and loads forms actually what we call the domain. And within this domain, the optimizer is free actually to remove or restore later material or finite elements. Okay, I would just like to quickly illustrate a very, very quick and short example. Let's say this is some bracket and the blue region is intended for optimization. And if I run the optimizer, you will see that the material will be removed where it is the least usable. If we switch to stresses, we can also see that the stresses are nicely evenly distributed within the optimized part. Okay. Now, what might be worth to point out is that although it seems that in this region there is no more material, I have to say that the finite elements, of course, are still there. And for example, if I just increase the required volume of that part, and if I run the optimizer, the material is restored back again. Okay, so switch back. Now, topology optimization problems can be formulated in many various forms or types, and I would just like to present maybe the most important one. And this problem actually covers maybe 90 or 95% of all topology optimization jobs. It is a static problem of strain energy minimization. Now, minimizing strain energy might sound a little bit weird, but at this point, it is really important to note that strain energy minimization comes automatically with some very, very attractive collateral effects. Namely, we get automatically high stiffness of the part. We get automatically practically, okay, not mathematically, but practically the lowest stresses attainable, and we get a design without stress concentrations. So if I say without stress concentrations, I mean, of course, in the region where the optimizer can actually do something. We call these surfaces where material is actually cut, the cut surfaces. So cut surfaces will for surely, if the optimizer is a good optimizer, will for surely be with nice evenly distributed stresses and without stress concentrations. Now, what might be disturbing for an engineer on this picture is this here. Now, at this point, I would like to note that this is not misbehave of the optimizer. This is a region where the optimizer is actually not in a position to do anything useful. No optimizer can solve this. This is actually a consequence of a poorly designed domain or poorly designed initial part. So maybe this should be kept in mind that when we prepare the cut model for the part to be optimized, we should be really careful about how to design the parts so that such things will not happen. So this static problem is actually discovers most of the topology optimization problems, and maybe the second most important one is the model eigenfrequency problem, where material is redistributed in such a way that the lowest eigenfrequency of the part is maximized. Now, it is not so often that this problem is solved directly. Typical jobs looks in a way that we also advise our customers in that way. Always the static problem should be solved first, and when we get a nice design, maybe it is time to check for the eigenfrequency, and if needed, then combine these two problems in order to get some maybe somewhat higher lowest eigenfrequency. A good optimizer can combine this very well. I will show you this later. Okay, now we are at our main topic, and this is how to engage topology optimization successfully. Now, there are quite some issues that actually have to be addressed very carefully, and I will go through these issues one by one, and I will also run example problems to explain what is actually the point. So let us start with the first. We call this interactivity. Now, unfortunately, a lot of topology optimizers is built in a way that you have to assemble all the objectives, requirements, constraints into one basket, and then you run some black box program, and then you just have to wait. Whatever comes out, and if you have to change something, then you have to start all over again. Now, I have to say that in this way, it is extremely difficult to get a real good design, because although topology optimization is theoretically rather simple, it is actually amazing how tricky this gets in real life environment. So this is the main reason that ProTOP is actually designed in the opposite direction. It is designed to be as interactive as possible, and we always advise our customers to build their optimization problems gradually. So I will show this on an example, what I am meaning with this. Okay, let's say we have some part here. This is some bracket, and we always advise the customers to start with some moderate, not very fine mesh, maybe moderately rough. And at the beginning, you should not apply any constraints, requirements, maybe just the basic load cases, the prescribed load cases, and run the optimization just to see what is going on actually. So this should be the first step, just to see how the optimizer will perform, and maybe to observe a little bit the flow of the stresses. Now, within this stage, if you encounter maybe a solution that is weird, or it looks very not good from the engineering point of view, this is surely a sign that load cases are missing. So if the first run should turn up something or bring up something weird, the first thing one should do is go back and check the load cases. In topology optimization, it is of extreme importance that every possible loading situation is actually contained within the load case. Okay, now I will pause this. let's say this is something that we are now satisfied with. And let's now see what interactivity actually means. Now, let's say we have 3 connections here, and maybe, let's say for me, this is a little bit too fragmented, and I just want to reduce the design fragmentation and maybe get rid of 1 or 2 connections. A simple trick I can do if I have an interactive optimizer is just to reduce the volume and run the optimizer. So as the volume decreases, the most thin connections will actually eventually disappear. And once this happens, I can simply increase my volume back again. And in that way, I can get rid of, these really tiny connections that might be very difficult to produce or would not be actually very useful in real environment then later. Okay, now I will just pause here. So now we have a little bit less fragmented design, and let's say we are now satisfied with this. But if we look from the bottom, this is not really symmetric, but we would like to have this that way. Okay, no problem. We would like some symmetry. We can just end the session, go back to optimization model, technological constraint, add a new constraint, plane symmetry, apply to the lower plate, and the normal direction should be Y, and close and OK. So I added a symmetry constraint, and I will run my optimization again. Now, to be able to really build your problem gradually, you have to have really nice restarting possibilities. I could simply restart my previous session that I have run, but in this case, I actually changed the finite element model. I added a constraint, the optimization model, sorry. I added a constraint, and in this case, I can simply say start from another session. I will pick this last one. And the optimization, sorry, is started right from where I have left in the previous optimization run. So the design will be symmetrized slowly. Okay, I will wait just a bit. Okay, let's say this is okay for us. Okay, nice. Let's say we are now quite content with our part, but maybe, okay, the part is loaded with 2 load cases. I can illustrate one load case in this direction, and the other load case is in that direction. Okay. But let's say I might be interested also in the eigenfrequency of this part. No problem. I can just close this, go back to FEA model, load cases. I will just add another load case. And this one should be of a model type. Okay. Optimization session. Of course, I would like to start from the last result I had. I will pause this immediately. Okay. Now, if we look at the load cases, we can see that, okay, these 2 are the static load cases that were here already in the previous run. And this is the new one. It is of the eigenfrequency. And the eigenfrequency of this part is now about 306 Hertz. Now, if I want to change this a little bit, if I want to raise this eigenfrequency a little bit, I can just use this slider here to put more weight either to the stiffness of the structure, this is actually strain energy minimization, or to maximizing the eigenfrequency. So let's say I will just put a little bit this, And as the optimizer runs, you will see that the eigenfrequency will increase a little bit. Oh, sorry. Okay, about 5, 6. Okay, it will be around 350 or 60 Hertz. And okay, let's say we are now quite happy with this result. I will just finish this. Okay. So this part now has a very nice stress distribution, and it has a frequency that is high enough. Just the problem now is that we have voids here, and this might be somewhat difficult to produce. Okay, no problem. We just go back, optimization model, technological constraints, and I will add a new constraint. This one, bidirectional opening, applied to the wall, and the normal direction is Y. Okay, okay. Now you will see now, I hope you can see now that the voids now will be filled nicely so that I can really get the design that I actually need. Okay, let's say this is fine now with me. Okay, let's say this is now a design that is fine with me. And before we end this, we should remember that for efficiency reason, the mesh that we used was maybe somewhat rough. And before this goes to some further processing, we strictly advise to take a really fine mesh and, just to polish the final result. Now in ProTOp, this is also quite easy. I just go back, FEA model, mesh refinement. I can simply choose what I want to refine. Let's say I want to refine just this wall. Analyze, and if you look here, here is the data about the edge length of finite elements involved. So edge length of a finite element is a very important data, especially if we will be doing shell lattice structures. This will be shown later. And now I have the possibility to say, let's say I just want all elements to have edges at most 2 millimeters. Okay, let's increase this a little bit and just refine. So we got a new mesh now, much finer. And I can go straight back to the optimizer, start from another, and I will just pause this immediately. So now I have the design that I already computed, but now with a much finer mesh, and really to polish, to finalize the design, this should always be used to run at least a few additional cycles, just to see if nothing of no surprise happens, and just to make the boundaries really nice. So, okay. So we are finished with that example, and I hope that I could show you what we actually mean by interactivity. So I have to say, even that we have a lot of experience with running optimization problems, and we never built a new problem directly, just put everything inside. We always do this cyclic way of try, check, adjust, and this is actually the only and actually very efficient way to get a good problem formulation and a good result. Okay, so this was the first topic, and we are at the second one. And the second one is actually related to efficiency. we have to remember, okay, the examples that I am showing here are really small. We have maybe 500,000 or more, a little bit more finite elements, and these are really small examples. You have to think about models with tens of millions of elements, and great care should be taken to perform or to make the computation efficient. So a good optimizer should offer things that can really make the running times acceptable. For example, to illustrate this, I would like to show you, for example, the semi-contact special finite elements engaged in ProTOp and what this actually means. Okay, just to start. So, this is some part, actually a quite simple thing, but let us look at the details. Okay. So this is the bolt that fixes. This is the bolt that fixes the housing to the base plate. This is the base plate, and these are the pins. Now the housing is fixed with a pre-tangent bolt, so that between the bolt and the housing we actually have a contact situation. So this is this dark gray layer here. The housing is also supported at two surfaces, so we again have two additional contact situations here and here, and the pins are also in a contact with the housing, so we have additionally contact situations here. Now, if you look at this part, it is actually a very simple part. It is loaded. If I draw this a little bit, this pin in that direction and this pin in that direction. Okay. But if you look carefully, we have 1 to 5 contact situations. Now, the usual way, if your optimizer does not offer something special, you would have to model this as a usual contacts. Now, if we do this step is actually devastating in regards to performance, because the computation time is actually increased by an order of magnitude. And the second problem is that once we have contacts, we will run during the optimization session at least once or a few times into a no convergence error related to the contacting surfaces. So this will be very difficult if we use usual contacts. Now, if you have something like these special semi-contact elements in ProTOp, you just have to model, you have to prepare your cut model so that you have fine, thin layers in the contact region, and you just declare these elements to be semi-contact elements, and that's all. Now, if we run the optimization, we will see from the resulting design that the contacts are nicely taken into account, while the computation itself is as fast as with normal usual linear elements, so there is no speed penalty, and there is absolutely no problem regarding to convergence, because nothing has to converge here. Okay, if I just rotate this a little bit and maybe switch to the stresses. So you can see that material is remaining here in that region, and if I would change this contact material to a usual material, this would disappear everything. So Okay, so I will just pause this. Okay, so much about special custom finite elements and algorithms. The next topic is something that we call design space configuration. I think, to my knowledge, this is a feature that is completely unique to ProTOP. It is actually a possibility to configure a solid part as let's say, a shell or lattice or a combination of this structure. Now, the purpose of engaging configurators can be various. For example, one of the most important probably is that shell lattice configure design might be much more robust in the sense that if the loading specification is not completely clear, or there are situations that simply you do not know how the loading will be, a lattice design might actually prove to be much more robust. The other reason is that this can be used to enforce special design requirements. And for example, in ProTOP, this can also be used to speed up the optimization process. ProTOP is built to be extremely efficient and fully focused on performance, and it can take advantage of every situation. And the lattice design structure has already initially a lot of void elements, and this makes in ProTOP the computation much faster. So, okay, to the example. So we have here a usual solid part, so completely filled with material. And let's say the blue region is free for optimization. I can just run this quickly to show you that this is usual solid part, and the optimization will start as expected. So some material is removed. Okay, I will this end now. Okay, one possibility is to optimize the part as a solid part, but in ProTOP, what we can do also is to configure this part as something else. Let's say to do this, I just add one configurator. Let's say this should be of a shell type, and the data is actually, I have to choose an appropriate surface that I want, and I have to enter the limits of the shell. So how the minimal thickness and the maximal thickness. And if I check this, I have a shell something like that. So I will have a nice shell-like structure. And let's say now I want to fill the interior with some lattice. Okay. I just add another configurator, and this one should be of a lattice type and the corresponding data. Of course, I have to choose the volume, the region. I have to choose the cell type, for example, a honeycomb, and I will set the limits of the lattice, let's say from 5 millimeters to, let's say 8, I don't know. So if I check this, so I got something like that. Okay, it is very easy in ProTOP to change everything. So let's say I would just like to translate this a little bit in the vertical direction. So I can incline this, I can shift this, I can impose as many configurators as I want to one over another. So there's really a lot of possibilities how to configure your design. But let's say we will be happy with this now. Okay. So let us take a look what we have done. If I run the design analysis, So this is now my configured design. And the optimizer is now free to do anything. This means either remove or restore material, but only within the limits. So the lower limits is this, and the upper limit is this. So within these limits, everything can be done. Okay. And to see how this functions, I will just run the optimizer. Just run the initial FEA. Okay. Now the configured design is immediately ready for optimization. So I just have to go to optimization and run it. What I want to show you is how quickly the stresses will decrease actually as the optimization will run. So I will fix this scale at 110 megapascals. Okay, I will now run the optimizer. This will go rather quickly, only a few steps. The material is redistributed. Some of the lattices will attain its lower thickness and some will become thicker. In any case, the stress concentrations are very efficiently removed. Of course, the highest stress we have here, but here is actually the limit, so the optimizer cannot do anything useful here. In any case, I hope you can see that the stress has really decreased and the design is actually, the optimizer is actually finished. Now, at this point, I would like to note that the mesh that you see here is far too coarse for such an example. So I use such a coarse mesh because it runs very fast and it is nice for presentation. But in real life, the mesh would need to be much finer. Okay. So much about design space configuration. Okay. Let's go to the last but one topic. And this topic is about design enhancement options. We internally also call this numerical candies. And although this might sound somewhat funny, it is actually very usable. And just to illustrate what such things can really mean, I will show you something that we call relaxation by virtual plasticity. Okay. So we have a nice part here. Is actually quasi two-dimensional. It is loaded here in this pin in the vertical direction and this pin in the vertical direction. So, okay. I would like to draw your attention just to the materials involved. The blue region that is actually will be optimized is selected to be a semi-plastic material. I will explain later what this means. Just that you know that this is now the choice for our optimization material. Okay. Let us run our optimizer. So the blue region is a semi-plastic material, but at this time I will leave the semi-plastic material model option disabled. This means that the material that you see, the blue region, will behave as a usual linear elastic material. Okay, so I will run the optimization. This should be rather quickly. There are only 270,000 elements. Okay. So I will switch immediately to the stresses. Okay, we should be done very quickly. It's important now to wait really until it is almost, at least almost finished. Okay, I think we are done now. So, okay, now I will switch to the custom scale and look at this region here. This one. Okay, I will scroll this down. And okay, if I'm seeing this correctly, the highest stresses are about 386 megapascals. Okay. So if I look at this design, I have to say that the optimizer has done its job flawlessly, so no problems here. But if I will show you this to some engineer, he will say, oh, this is a problem here, this is not nice. So what to do now? ProTOp has very nice functions for that, and this is called relaxation by virtual plasticity. Okay, I will just enable the semi-plastic model, and because the stress levels is about 380, I will define that the material here can yield at, let's say, 160 megapascals. Okay, I will just run the optimizer. And as you can see, the stresses are of course reduced because the material yields. But what is important is that material is added here in the background, because in the foreground the material is relaxated. Okay. So we are almost done. Now, the stresses on the picture are now much lower, but this is of course fake, because we actually declared that this material yields at 160 megapascals. So this is not true. Now, to check the actual situation, I will now switch off the semi-plastic model and run a usual FEA analysis. Okay. Now, let us take a look at this region here. Now, previously we had 386 megapascals in this region. Now the material was a little bit redistributed, and we have now stress levels about 317. This means that we are about 65 megapascals down with maximal stresses. 65 megapascals is really a lot for such a part. It can mean a difference between a lifespan of, I will just say so, 100,000 cycles and maybe 1,000,000 of cycles. So the order of magnitude of the lifetime of such a part can change by decreasing the stresses in this extent. Okay, I will just close this. And we are now at our last topic. This is related to precise export surface finalization. So every topology optimizer, the result that it produces is actually a surface, and this surface is typically exported as a triangulated surface. Now, what we do with this surface is another topic, but what the optimizer has to assure is that the surface can be, of course, nicely smoothed, and, which is very important, this smoothing has to be done accurately, because if the changes of the geometry are too large, and this happens very quickly, the engineers are typically very sloppy about this. If the geometry changes too much, even if it looks nice and nice with curvature, the stresses can increase very quickly in a significant extent. So one really should be careful about this. Okay. Now, just to illustrate a little bit the tools that are used in ProTOP. So ProTOP will for surely export an error-free surface so that we got a triangulated surface with no errors. It will be a closed surface so that it actually represents a solid body. And it also can be nicely smoothed. For example, if we select just the cutting surfaces, remove a little big peaks, I will just run the most basic operations a little bit. Okay, a little bit simplify, refine, and smooth. Okay, so we can get really quickly, I didn't bother a lot with this, but you can really get really nicely smoothed surfaces very easily. And ProTOP makes sure that the geometry distortion is really kept at some minimum so that the exported surface is actually a nice surface. So the last thing to end is to export this surface, and we can either go directly to export into some, let's say, STL, OBG, STEP, or AMF format, or eventually, if we want to take this geometry into some, let's say, freestyle modeler, then the triangles should be reduced drastically. This can also be done in ProTOP, for example. Okay, so exporting this surface would actually finalize our optimization job. Okay, so we are actually done. What I would like to show you at the end is I have shown you some actually really small examples. 500,000 of elements have been run. This is the maximum I have shown so far. But please do not get the wrong impression that ProTOP is only for such Mickey Mouse problems. In reality, what runs very efficiently in ProTOP are examples like, if you take a look here, this engine hood. The model contains about 57 million of elements, and we have about 20 load cases. So you can imagine that having in such a case something like, maybe you can see it, maybe not, something like automatic load case management, where the optimizer takes care which load cases can be skipped to save CPU time. Having something like that in such examples is very important. So this is one interesting example. ULA bracket is another one. Here it was allowed to design a part that will be 3D printed, so a lattice structure was allowed, and the part could nicely be optimized with one shell and one lattice configurator, and the model also contained about 25 million of finite elements. So this axle shaft carrier is also a nice example. This is an extremely low volume study, so we wanted to see what it comes out if we go down to 7% of the initial volume. Okay, maybe the last one, some hydraulic valve housing. This is an interesting example because this is actually a solid part optimization, but to get what we actually really wanted, we had to engage a shell configurator. So these configurators are really useful, even you see in situations when solid optimization is done. Okay, thank you very much for listening, and I am done. Barbara?
Thank you, Marco. That was great. Thank you for walking us through these optimization examples. I'm waiting for a few questions. If anybody wants to raise their hand. Okay, we have one question right now. Great presentation. Doesn't stiffness attract more load? So when saying stresses are lower, is it because the members that are stiffer get bigger? That's question number one.
Okay, I will just, let me see if I have. Okay, now this is not very good. Okay, I can use this still one. Stress distribution. I'm not sure if I understand this well. I will try to answer. When topology optimization runs, material is redistributed, and material redistribution also induces the flow of the forces. So typically, the loaded, of course, it may happen that some of the loaded regions really take all the load, and these are actually stressed more. But mainly it is the material that is removed could actually not be stressed at this particular level. So it is actually removed the material that would ultimately be inefficient in some way. So it could be present, but it would be loaded with low stress levels. And if you want to get low volume design and lightweight design, we really have to keep just those regions or those sub-regions that can really carry the load. I don't know if this was exactly the question, so...
Well, let us know if Marco got it right. In the meantime, this particular attendee has more questions, so we'll see if in the meantime he can reply and let us know if we get it right. So question number 2, I also shared with you on your chat, so you can read it as well as hear it from me. Can no tension members be specified or a limit on tension?
Sorry, can you please repeat this?
Yes, the question is, you can read it if you look on the control panel. Can no tension members be specified or a limit on
just
tension?
a moment.
Yes.
I have to expand this a little bit.
Okay.
Sorry.
Question number 2. That's
just a moment. Number 2. Oh, this is no. Can no tension members be specified? What does it? Actually, if I understand this,
I think he means for example, no capacity to handle tension stresses. So material is optimized for compression only.
Okay, what you can do is actually, sorry, I will have to run another. What you can do, this will be quickly. So
sure.
I haven't loaded this one because, okay, this is a quasi two-dimensional example. I will run this quickly. This is something, this is actually a two-dimensional cantilever. Oh, sorry. This is already material model. This was already changed for that reason. Okay, I will run first. This is actually a cantilever. It is supported here and it is loaded in that direction here, a point load. Okay. I will just run this. I will switch to stresses, and not only stresses, I will switch to signed Mises stresses so that we can see where we have tension and where we have compression. Red color is tension and blue color is compression. Now what you can do in ProTOP is actually, okay, let's say we are done. I will end this. You can say, for example, that your particular material does not behave the same in tension and compression. Let's say that you want to have lower stresses in the tension region in order to make the design, for example, safer against crack initiation. So let's say you say factor of less than 1, let's say 0.6, means that you will allow, let's say, 100 megapascals in tension, but only 60 megapascals 100 megapascals in compression and 60 megapascals in tension. Okay, so if I run this last, okay, you can see now that the material will be redistributed. The tension region will become actually thicker, and the compression region, the compression region will become thinner. So if I scroll this a little bit down, you can, okay, we switch to AM stress. Now you can see that the stress levels in the compression region is higher and the tension region exhibit lower stresses. So this is a possibility that you can do in ProTOP. Okay.
All right. Cool. Can you?
Number three. Number three, can a material like concrete with compression and reinforced steel tension only be simulated? It looks to me this is a similar question. What ProTOP can do at the moment is the materials that are actually considered are homogeneous. So you have to model concrete, even reinforced concrete, as a homogeneous material, if this is possible or acceptable for you. And what you can do regarding this tension and compression is what I have already shown. So you can require that the stresses in the tension region will be lower than the stresses in the compression region. I hope this was number 3. What is the tool that is used for this? Now, what is the word "this" related to? Do you know, Barbara?
No, this is a webinar on ProTOP. So if that was your question, this is the answer. I don't know if it refers to a specific feature, but let us know.
Okay, maybe I could just tell us some words about ProTOP.
Okay. Software tool. Yes, that's it. So yes, it's a ProTOP Professional. And if you stick around, we'll show you how it looks on our catalog and where to find it. So yeah.
Okay.
And how does it behave when it's for composites? What about composites? Are there big differences?
Regarding the material models, I have to say that currently we have only homogeneous models, and of these we implement isotropic material and orthotropic material, but these are all homogeneous material models. So if you are able to model your concrete material or part of your material as a homogeneous material, with averaged properties, then this would be fine. But ProTOP is not capable to model, specific materials with, I lost the word. with fibers or something like that.
Cool. And can ProTOp work with geometry from Rhino Grasshopper for nicer imports of complex geometry?
Just a moment. What ProTops, how it can actually be engaged now. I will show you this. Just a moment. Okay. How ProTOp actually operates is that it has to get the input from the input is a complete FEA model. That means a finite element model with boundary conditions. That means supports and loads. And this FEA model can currently be prepared either in PTC Creo. From PTC Creo, ProTOp can actually be also started directly from Creo's toolbars. Okay, the FEA model can also be prepared in Simulia Abacus and exported as an IMP in SolidWorks, simulation, and Siemens NX. So these are currently the modelers or CIA software where the FEA model can be prepared that can be imported into ProTOp.
Cool, thank you. Okay, and now the million-dollar question. How is ProTOp different from other tools such as ANSYS? What are the biggest?
Okay, just a moment. Now, actually, the strengths of ProTOp is mainly what I have shown you here. First of all, I want to point to this interactivity. As I said, most optimizers, to our knowledge at least, are built so that you have to specify everything, all objectives, requirements, etc. You have to prepare your model, and when you have the complete package, you run some batch job, and then you have to wait. And at some time, something comes out, and when you want to change something, you have to change this, and you have to run again everything from scratch. So because getting the optimization model really right so that it is well defined and it actually returns a good result is a very tricky business. And if you have only this, this batch job way of doing this becomes incredibly difficult. So ProTOp is really focused on this interactivity. It has great restart options. You can optimize today. You can close ProTOp, come back the next day and run the optimization from the point on when you ended yesterday. You have great restart options. You can even record your design cycles. So, when you make experiments, try this and that, and maybe at some point you get a result that is worse, that was some previous results, you can easily go back, load the previous result, and just continue your optimization. I think this is incredibly important. Now, this option to be operationable, the software has to be incredibly efficient, and ProTOp is built, it is all about efficiency. So it contains a myriad of tools, and each piece of code is actually very carefully designed to be parallelized to the maximum so that everything really runs as it should. It contains the second thing is it contains special custom elements. So we don't engage regular elements as usually our competitors. Also, the ordinary elements in ProTOp are specially developed and coded for ProTOp. So they contain special enrichments to enable nice element cutting, and so then I think this is really unique, this shell lattice tool configurators. I don't know any software that has this. Some software offer to generate some lattice structure. But to my knowledge, in such cases, this lattice structure is modeled by beam elements. Once you do this, this is a completely wrong way, because you will never get rid of the stress concentrations if you employ beams. This is not possible. You have to go with solid elements, and I think ProTOP is the only one that can do this. So I think I never seen at any competitor such this result and have enhancement capabilities like this virtual plasticity. So to my knowledge, no one has this, but these are maybe such things, we call them numerical candies. This sounds a little bit funny, but they can be really, really important. Okay, that would be the main.
Yeah, wow. Yes, that's great. Good to hear. Good to know. And I don't see. Okay, one more question. When we hear FEA, the first thing that comes to our mind is mesh size.
Yes.
Please explain about meshing in ProTOP.
ProTOP does not have its own. ProTOP cannot do cut work, so you cannot define a cut model within ProTOP, and it does not contain tools for generating a FEA model. So meshing cannot be done in ProTOP. Applying boundary conditions cannot be done in ProTOP. This is everything. This everything is expected to be brought as input from, for example, from this software. But what ProTOP can do is localized mesh refinement, and you can do this between during a session run. You can just stop the session, refine the mesh, and then continue optimization. And this mesh refinement can be localized to the region that you want, and it tells you exactly what the edge lengths of the finite elements are, so you can set this precisely to your needs. For example, if you do lattice configuration and the thickness of a lattice bar is 3 millimeters, then you cannot go with edges longer than 1 millimeter. You have to set this precisely. And ProTOP enables you this to do very efficiently, and it can also handle large meshes. And in topology optimization, the elements at the end, when you finalize your result, the mesh really has to be fine, because it is actually the same as in digital photography. If you have a pixel 1 by 1 millimeter and a picture size of 10 centimeters by 15 centimeters, you cannot get a nice picture. This is impossible. So you have to have really fine pixels, and in topology optimization, this actually translates to fine elements. So there is no way actually around fine elements.
Thank you so much, Marco, for answering all your questions. We're taking just one more. Is ProTOP all about post-processing?
No, I would not say. It is actually a designer tool. It has very capable FEA solvers with specialized elements. It has additional tools, for example, enforcing constraints and such thing. I wouldn't call it a post-processor. The input that it gets is actually a usual FEA model, and what it produces is a design that is actually, if you made everything correctly, that is exhibits lower stresses and no stress concentrations, etc. So I wouldn't see it as a post-processor.
Yes, don't get the wrong idea. This is a designer tool.
Yes.
Yes. Thank you very much. Everybody, I think, is giving great feedback, Marco. I'm taking the screen back just for a second. So I want to show everybody who's on the market for a highly efficient topology optimizer to come over to Novedge and check out ProTOP. And here's the product page. You can our search is huge. So there's a lot of products. We also sell Creo and some SolidWorks. So you can find a lot of tools for your design at Novedge. And thank you so much for attending today. And if you missed something, you can always find the recording of this webinar on our Novedge and YouTube channel. Thanks again for joining us today. Thank you so much, Marco. This was illuminating. And
Thank you, Barbara.
thanks, everybody, for joining us. Have a great rest of the day. Bye-bye.
Bye.